Hi everyone. So this is part 2 of chapter 2. This is our unit conversions. So when doing unit conversions, we have to understand a couple of different things. Unit conversions is learning almost like a new language, a different way of representing something we already know. So, for example, different countries use different kinds of currencies. Some countries use pounds, others use ounces, whatever it is that they might think of to represent the same thing, right? So, how many miles per hour or how many meters per hour, things like that. So, when you're traveling and you're like, oh, well, what is the distance? What is the price? What is the weight? You have to learn how to convert in order to figure out something that you're used to. So whenever we do a math problem, we also must represent the unit that is associated with that math problem. For example, in this case, we have a nice little block, right? And we could take this block and we say, okay, this block is 10 by 10. Well, 10 by 10 what, right? So I could say that this block is a 10 by 10, and that would give me 100. But 100 what? 100 inches? 100 feet? 100 meters? If you don't say what the unit is, then you don't know what exactly you're measuring, what the quantity is. So you have to state your unit with your answer. No unit gives you a wrong answer. So when you are doing your homework problems or anything like that, or in the future you're calculating, make sure you always state your unit. Do you want $100 or 100 cents? Right? Like you get 100 pennies and they're like, you said 100 and I gave you 100 pennies. Is that the same thing as $100? It's not, right? It's very different. So always make sure you include the unit in all the work that you do. Okay. All right. Now let's look a little bit more. In this case, this one is 10 by 10 feet, right? So we have feet and we have feet. So we get 10 feet by 10 feet. And we would say, okay, this is 100. But is it just 100 feet? We could see that it's not, because we're going to take feet and multiply it together. And that's what's going to give us feet squared. Okay. All right. Looking at our next example, this is using smaller units, right? So in this case, we have 15 milliliters and we're going to convert it to milligrams, and most likely using density, right? The calculation for density. Milliliters cancels out and you're left with 15.3. But 15.3 what? 15.3 milligrams, right? So when you state your answers, state the number and the unit. Right? You have to have the correct number with the correct number of significant figures and the unit. Okay. So dimensional analysis is just a way of saying conversions. We're converting, right? So dimensional analysis converts simple numbers, simple things. Stoichiometry, which we're going to get into later on, is a little bit more in depth, more involved, right? It relates more to the science, while dimensional analysis relates more to the everyday things that we can see. It also involves the metric system. If you're not 100% familiar with the metric system, I do recommend you do review the metric system a bit on your own. There's some great YouTube videos on conversions with the metric system. Okay, so a copper pellet has a mass of 231 milligrams. What is the mass in grams? So we currently have 231 milligrams. We want the mass in grams. Remember, mass is represented with the unit of grams, unless stated otherwise. So we need to learn the conversion between milligrams and grams. The equivalency between milligrams and grams based on the metric system is 1,000 milligrams is equal to 1 gram. This is called the equivalency, right? So what this means is when we're ready to use this as an equation, we could write it as 1 gram divided by 1,000 milligrams, or we could say 1,000 milligrams in 1 gram. Now you could also do this differently and use like 0.001 gram in 1 milligram. However, I like to do it this way. It helps me remember. The bigger unit gets the 1. Always remember that. The bigger unit gets the 1, and the smaller unit gets the zeros. Okay, because the smaller unit, you need more of those to make up 1 of the bigger unit. Whenever I think about it like that, I always tend to get it right. If I start doing the 0.001s, I personally get confused. So this is how I learn. This is how I'm teaching you. If you learn the other way, by all means, that is totally okay. All right, let's go ahead and set up our problem. Always start with your given. We are given 231 milligrams. We're going to convert it to grams. So if we set up our problem, okay, we are going to bring this unit down, milligrams to the bottom, and the unit that we want on the top, grams on the top. Why? Because if we have milligrams on top and milligrams on the bottom, they divide into each other and they divide into the number 1. So for example, if you have 2 divided by 2, this is equal to 1. If you have 100 divided by 100, that is equal to 1. X divided by X is equal to 1. Milligrams divided by milligrams is equal to 1. So when we reference something and say these cancel out, we are saying that they turn into 1. So let me get a different color here. These units are going to cancel out. And now I'm going to write my equivalency factor. Right. So I have 2 equivalencies. I have the 1 gram over milligrams, or I have the milligrams over grams. Because we already wrote our problem out, I could already see that the 1 goes on top and the 1,000 goes on the bottom. Now my problem's quite simple. I'm going to take my 231 and I'm going to divide it by 1,000. And then we can see what we get. Now, a simpler way to do this, instead of having to write it in your calculator or anything, you see that you have 3 zeros, 1, 2, 3. Bring that 1, 2, 3. So take your understood decimal, which is right there, and just move your understood decimal, the number of zeros that you have. So you're going to move it 1, 2, 3, 3 spots, and you get 0.231 grams. Okay. All right, let's see how we did. Okay, we have our equivalency factors. We take our 231 and we divide it by the 1,000 milligrams. And we cancel out our units and we get the 0.231 grams. Okay, this method that I used right here, it's called the factor conversion method. The factor conversion method. Okay. And that's a factor that we tend to use in science to keep our work organized. We know that you multiply everything that's on the top and you're going to divide by everything that's on the bottom. So multiply by whatever's on the top and you're going to divide by whatever is on the bottom. All right, let's look at our next problem here. How many inches are in 236 centimeters? Pause it, try it out on your own. Let's you and I go ahead and try it. Now that you've unpaused it, I hope you paused it and tried it on your own first. You have 326 centimeters. Okay. So how many inches? That means we want to go from centimeters to inches. The conversion factor is already given to us. Look at that. Write the conversion factors down in your notes. You never know if you're going to use this or not. So the conversion factor, or the equivalency, I apologize, this is the equivalency. They're turning to conversion factors when we put one on top of the other. So we have 254 centimeters over 1 inch. So let's go ahead and write them. 2.54 centimeters divided by 1 inch, or 1 inch divided by 2.54 centimeters. Okay, so these are our conversion factors. Right, to go to inches to centimeters. Now that we have those down, let's go ahead and write out our problem. I like this pen or stylus that it has. It makes my writing look really, really nice. I can't write that nice. All right, 326 centimeters. I'm going to use the factor conversion method because it makes everything look nicer. Centimeters goes to the bottom because I want to cancel it out. Shing! And you have to say shing when you bring it down to the bottom. Why? Because it's going to make you remember it. 1 inch over 2.54 centimeters. What I want goes on top. What I don't want goes on the bottom. Now that I have that down, I'm going to go ahead and cancel out. Oops, that was the wrong one. Cancel out the centimeters because I have one on top and one on the bottom. And if we recall, centimeters divided by centimeters is equal to 1. So they cancel out into the number 1. And anything multiplied by 1 is the same number. Anything divided by 1 is the same number. So now you don't even have to worry about it, right? That unit is now gone. We are left with 326 divided by 2.54. The unit that we're left with is inches. So whatever answer we get here, we're going to get it and turn it into inches. I'm going to grab my handy dandy calculator and put this down. I have 326 divided by 2.54. And I get 128.3464567 inches. Oh, look at that. I'm totally done. No, we're not done. All right. If you write this down as an answer on any of your problems, it's going to be incorrect. You're going to lose points. Why? You're not that accurate. The original problem that you have, right? They gave you 3 significant digits right here, 3 significant digits. And this answer, everything in the calculator tells you that you're as accurate as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. That you're that accurate. There's no way you're that accurate. You're only as accurate as your least accurate number, and the least accurate number has 3 significant digits. Oh, what about our equivalency? Your equivalency factors do not play a role in the number of significant figures used at the end of your answer. Only what is given to you, only the variable that changes, not the equivalency. Your equivalency does not change. That is infinite, that stays as is. It does not take part in your final answer significant figures. All right, so with that being said, we have 1, 2, 3 sig figs. Significant figures or digits, they mean the same, right? You'll hear me switch from sig figs, significant figures, to significant digits. All right. So this one has 3 significant figures. 1, 2, 3. This one also has 3 significant figures. I just write 3 sig figs down. So that means my final answer also has to have 3 significant figures. Oops. Actually, what did I just say earlier? We do not take account the equivalency factors. So cancel that. We're only looking at our original. All right there, 3 significant. So we're going to go 1, 2, 3. The number next to our significant is a 3. So the number 3 cannot round up the 8. Okay, so this does not round out. I'm just going to drop all of that. And I end up with 128 inches as my final answer. And I'm going to box that baby up. When you do your answers, if there was a number on this one, I would write the number down. Okay. But right here, what I wrote down is partially the question. Okay. This is how many centimeters to inches. That's it. Okay. All right, we are at 128 inches. I feel like we did pretty good. Okay, what is this part here? 326 centimeters. Oh, this is showing you the incorrect answer, by the way. Look at this. If you were to use your equivalence factor in the other way, you're now taking centimeters times centimeters. So take a moment to think, what is the unit going to be here? Okay. If you did it the wrong way, you're going to get centimeters times centimeters divided by inch. Can centimeters cancel out with centimeters? No, they can't because they're being multiplied. Right? Let's do this in factoring conversion method right here. They're being multiplied together. You're going to get centimeters squared over inches, which would be incorrect. Right. Here's a problem. The speed of light in a vacuum is 3 times 10 to the 8th meters per second. What is the speed of light in miles per hour? Let's go ahead and write some stuff down. So speed of light. This is an equivalency. Meters per second, not miles, meters per second. What is the speed in miles per hour? So we want to go from meters per second to miles per hour. Okay. This is what we want to do. This is what we want. This is what we have, are given. Okay. We are also given the conversion factors. In 1 mile, there is 1,609.3 meters. And in 1 hour, there is 3,600 seconds. Let's go ahead and work this problem out. Right? Not hard at all. Maybe you haven't seen something like this before, but just know it's not hard. Start with your given. Always start with your given. Factor conversion method. Actually, you know what? Let me write this a little bit different just so you could see it. Okay. We have this, and it's in meters on top, seconds on the bottom. Remember, this is in scientific notation right here. This is a very, very, very large number. Okay. Now, what part do we want to do first? You could pick. You could either turn seconds to hour first or meters to miles. I usually like to start with the things on the top first. So I'm going to go ahead and convert my meters to miles. That means I'm going to use this equivalency right here. Since I want meters, actually, what do I want? I want miles. Since I want miles, miles is going to go on the top and meters is going to go on the bottom. Okay. 1,609 meters, 1,609.3 meters in 1 mile. This is going to allow the units of meters to cancel out with meters. If the unit you don't want doesn't cancel out, that means you're doing something wrong and you have to try it again. Okay, meters has canceled out. Now I'm going to do my next step. My next step is to turn seconds into hours because I want miles per hour. The equivalency is given to me. 1 hour is 3,600 seconds. So remember, I want hours and I want to get rid of seconds. Now, if I did this, is that going to get rid of my unit? Seconds is here on the bottom. And I wrote seconds right there at the bottom. Can those cancel out? No, they can't, right? You're going to get seconds multiplied by seconds. If they're next to each other, you multiply it. If they're top and bottom, you divide it. That will give me seconds squared. I don't want seconds squared, so I'm not going to do this setup. I want to get rid of seconds, so therefore, since seconds is at the bottom, I need to put seconds on the top. And now I'm going to put my hours at the bottom because I want the hours right here on the bottom. So I have 3,600 seconds in 1 hour. If I look at the units, do my units cancel out? Well, let's see. Seconds can now cancel out with seconds. Top and bottom cancel out. Can miles cancel out with anything? No. Can my hour cancel out with anything? No. I'm left with miles per hour, miles an hour, and that's exactly what I want right there. So with that in mind, I'm just going to go ahead and solve my problem. Now, some of us like to rework problems. So why isn't this writing? Hold on. Oh, somehow it got switched to white. Okay. I like to rewrite them sometimes, not all the time, but just for demonstration purposes. This is the top part. Now it's saying that I'm going to take this multiplied by 1 multiplied by 3,600. And I'm going to divide all of this by 1 second. I don't really need to write 1, right? I wrote this one just so you could see. Divided by 1,609.3 divided by 1. I'm not going to write it. Take your handy dandy calculator, and I'm going to take 3 to the 8th power times 3,600 divided by 09.3. And I get this lovely answer, 671099235.7. Oh yeah, I'm totally done. No, I'm not. All right. You know I'm not done. So let's go ahead and look at this. What are we given? We're given this, 3 significant digits. Okay, even though this is an equivalency factor, it is what's given to us as a conversion, right? So we're going to use this given conversion as our significant digits. 3. 1, 2, 3. There's a 0 right next to that 1. The 0 cannot round up that 1. Okay. Now, is this the correct answer? Right there? Am I going to leave it as that? Is 671 the same as this giant number? If you can't tell the difference, do this. How much money would you like to have? 1, 2, 3. 1, 2, 3. 1, 2, 3. Would you like to have this top one or that bottom one? Right? Now you could see the difference. You could totally see the difference. This is $671,000,000, and this is just 671. Right? You want 671 million, or do you just want $671? I don't know about you, but I rather learn how to do a little bit of math just so I could figure out that this is the amount of money I'd rather have in my pocket, which I don't, but I'd rather have that than this. Okay. Now that we got that out of the way, let's go ahead and write it in the correct way. 3 significant digits. That's not it. So I'm going to need to represent the rest of those numbers. So I'm going to put it in scientific notation. 6.71 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. And now I'm going to include my units, because if you don't include your units, then what do you got? 6.71 times 10 to the 8, what? Meters? Miles? Right? You did all that work for nothing. So include your units. Miles per hour. Box up your final answer so I could see it, so everybody else could see it, so you could see it and you could verify it that you did your problem and you did it correctly. Let's see if we did it correctly now that I talked all this. Let's see. Da, 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 da. All right, not so bad. Look at that. I still got it in me. Okay. Ooh, what's this? Similar type of problem, but now instead of talking about the lengths, right? Distance, length of something, now we're going to talk about the volume. How much space is something occupying, right? Volume. It's the amount of space an object occupies, okay? Or can hold. the amount of space an object occupies there that it could hold, right? So if you got a water bottle, a basic water bottle is 8 ounces. The volume is 8 ounces. But you could have one that's 16 ounces. That's bigger. It occupies a bigger volume, right? Okay, let's go ahead and now look at this cube. We have a lovely little cube set up, okay? And in our cube, see if we could draw it right there. We have 3 different lengths. Length number 1, I'm going to call it A. Length 2, I'm going to call it B. And length 3 is C. The basic equation for a volume, which is how much space something occupies. Let me see, get a helpful highlighter. I want to know how much space is occupied inside of this cube. But the only way to know how much space that's occupying is to take the volume. And the volume of an object is equal to the length times the width times the height. Okay. So in this example, volume is equal to 10 times 10 times 10. And all the units are in centimeters. Okay. Now, we're going to get back to this unit. As you can see it there, we're going to get back to this. We have centimeters. Actually, I should write this differently to not confuse you. We'll write the units in a second. So we got 10 times 10 times 10. Well, what is 10 times 10 times 10? It's 1,000, right? So you're going to left with 1,000. Oh my God, 1,000 what? Right? We don't know. All we know is that A is 10, B is 10, and C is 10. So we look back at the example and it's 10 centimeters. Now, if I write 1,000 centimeters, is that correct? No, you're right. It's not correct. That's like getting a ruler and taking a one-dimensional distance. One-dimensional. This is 3. You're taking 3 dimensions. You're measuring them and putting them together. The volume. Okay, so we have 10 centimeters times 10 centimeters times 10 centimeters. So that is 1,000 over centimeter. Not over, sorry. That is 1,000 here. And this centimeters times centimeters times centimeters is centimeters cubed. They're not over something, I misspoke. So the unit is 1,000 centimeters cubed, right? Because you're multiplying all of them together. Okay. Centimeters cubed is the same as milliliters. 1 centimeter cube is equal to 1 milliliter. Okay, that's not our answer for this. This is another equivalency to know. Our actual answer is right up there. Okay, but this one is just an equivalency that I wanted you guys to keep a good notion of, because you may or may not use it. I can't remember. Okay, this is just the different ways of showing you when you're doing measurements, your unit matters, right? So let's say you're going to go into construction, you're going to go into the manufacturing business, you're going to be a laborer of some sort, you need to know your measurements, right? Can you actually transport something? Does it fit in your vehicle? Does it not fit in your vehicle? Is it small enough to fit in the box? Do you need a semi-rig? Do you need a trailer, right? Or is it so tiny that you could put it in a shop? Now, a lot of you guys want to go into medical school. Is the doses you give a child the same doses that you give an adult? Or are the doses different? What do the doses depend on? Do they depend on the weight of a person? That means you have to do conversions, right? So understanding your conversions is extremely important for the future that you're going to have. Because if you mess up the conversion, the doses for something, you could actually hurt or kill someone. So this is extremely important. Understand how to do your conversions and the differences in your units. You want to be good at what you do, start with the basics. All right. So Other unit conversions to look at. Okay, I gave you the 1 milliliter is equal to 1 centimeters cubed. What about if you had a liter? Well, 1 liter is equal to 1 decameter cubed. Decameter cubed. It sounds a little bit weird, but yeah, this is like 1 liter here. This is 1 decameter cubed. Okay, not deci, deca. Deci is a small unit. Deci is like 10 to the negative 2. Deca is 10 times 2, something like that. So different units. Okay. Oh, I guess to the third, my bad. So deca is 10 to the third. Okay. So you could see our units, our measurements matter, but we could also see that there is a way to convert length and volume together. Can you convert from one to the other? The answer is yes. They are convertible. Okay. What if you don't have this conversion? What if there's something else? So this is when density takes hold. Everything has a specific density. Okay. We're able to analyze things based on their density, know what it is by taking the mass of something and taking the volume. We can identify its density of an unknown object and match it and correlate it to stuff that we already know. Okay. How many cubic centimeters are in 1 cubic meter? Well, in 1 meter, there's 100 centimeters. So if you have 1 cubic meter, this is 1 cubic meter, then you have 100 centimeters cubed. I know, or cubic centimeters. I'm just used to saying centimeters cubed, but cubic centimeters, right? So if you have 100 centimeters cubed, that's the same as saying 100 centimeters times 100 centimeters times 100 centimeters. Well, what do you get? You get 1 million centimeters cubed. Okay. I know it's a little bit like tricky to go into, but look at the difference in parentheses. 1 meter to the third versus 100 centimeters to the third. These values are inside of parentheses. That makes a huge difference because now we're taking the value inside and multiplying it by itself 3 times, right? Take this value inside and multiply it by itself 3 times. If the number it's outside already, that means that you leave it as is. This is already 1 meter cubed. You're already taken. Let me go ahead and put this in. You've already taken this value and multiplied it. So 1 meter inside of parentheses to the third is the same as saying 1 meter times 1 meter times 1 meter. So what do you have? 1 times 1 times 1 is just 1. And you're left with meter times meter times meter. Well, meter times meter is meters squared times meters. That is 1 meter cubed. So this is the difference between how you write something. Make sure that you pay attention to how something is written, whether the parentheses is there or the not there, right? It makes a difference in your number. As you can see with this one, it makes a huge difference, right? We have 100 centimeters cubed. That's the same as saying 100 centimeters times 100 centimeters times 100 centimeters. Well, 100 times 100 times 100 is 1 million. And centimeters times centimeters times centimeters. Well, centimeters times centimeters is centimeters cubed. Squared. And this centimeters times that centimeters is centimeters cubed. Right. So that's just about paying attention to our parentheses. A hospital administers an IV fluid at a rate of 95 centimeters cubed per hour. How many liters of this fluid does the patient receive per day? let's go ahead and look at our information given to us. We know that we have 95.0 centimeters cubed per hour. This is what the patient is getting in their IV. Right? We want to convert this into, what do we want? Liters. Okay. Per what? Per hour? No, per day. So now we're going to convert centimeters to liters, and we're going to convert hours to days. Let's see if they give us any equivalency factors for us to be able to use. They did. And even if they didn't, we could always look these up and find them, right? Most of these are already common sense to us, so by all means. All right, the first one is something we just went over on the last couple of slides. It's converting centimeters into liters. Okay. Multiple step conversions are going to take in play here, or we could just shoot to this one. But let's pretend we don't know all that. Let's just have this one. We know this one. This is the only thing we could remember. All right, cool. Start with the top one. I'm going to rewrite this. I'm going to do the method, factor label method, centimeters cubed, and I want milliliters. Now I know that in 1 milliliter, there is 1 centimeter, right? Okay, let's say this is all I can remember, or centimeters cubed. In 1 milliliter, there's 1 centimeter cubed, okay? Right. This allows centimeters cubes to cancel out. Super easy, right? Now I can do milliliters into liters. I want to cancel out milliliters. I want liters. I know that in 1 liter, liter is the big one, there is 1,000 milliliters. That's the conversion factor we saw earlier. Milliliters cancel out. Now I have liters. I want that. Let's go ahead and just solve this first part. 95.0 times 1 times 1 is just 95. Divided by 1 hour times 1 centimeter divided by 1,000. And take my understood or my decimal, I could see it's not understood, and move it over 1, 2, 3 times. 1, 2, oh no, what do I do? Just move it over again, 3, and add a 0. So that gives me 0.0950. And my units don't fit right there, so I'm going to just rewrite this. Liters per hour. I'm not done because I want liters per day. Okay, I got the liters part checked, but I don't have this part done. So now let's do another conversion factor. I want to get rid of hours and I want to get to days. Well, we know that then 24 hours are in 1 day, right? With that being said, I can now cancel out hours. I'm going to take this number and multiply it by that number. So I cannot do that in my head. I'm going to go ahead and put it in a calculator. And that gives me 2.28 liters per day. This is the correct amount of significant figures. Well, let's see. I started with 1, 2, 3. My answer is in 1, 2, 3. I think it is. All right, let's see how we did. Oops, went a little. Here we go. All right. And look at that. We did really well. Okay. Now, theirs is shorter than mine because they use this bottom conversion. But like I said, what if we can't remember that in 1 liter there's 1,000 centimeters cubed? Well, you just take it one step at a time until you get to what you need to get to. All right, now we're going to go into mass and density, right? Well, we know that density is mass divided by volume. Mass divided by volume, okay? Or you can put M over V. Okay. Density is mass divided by volume, m over v. Now, one way to remember this in case you're doing something and you're like, oh my God, I can't remember. And I like to I learn personally by giving little stories about everything, and then the little story always happens to allow me to remember. So instead of saying density, I like to say destiny. And I want to say that Destiny was my best friend. Me and her were like BFFs forever and ever. And then one day, Destiny, I don't know, stole my lollipop or something. I don't know. But, anyways, she broke my heart. But in a samurai kind of way, she sliced it in half, right? Well, that left me with M over V, which separated my mass and my volume. I am no longer whole. All right. But that now allows me to be able to take destiny is equal to my mass divided by my volume. All right. Anyways, that sometimes helps people remember. I hope it helps at least one of you remember that destiny broke my heart. And when you break a heart, you're left with M over V, mass divided by volume. Okay. So let's look at this problem right here. A saltwater solution has a mass of 11.29 grams and a volume of 10.4 milliliters. What is the density of the solution? All right, so what do we have? We have 11.29 grams. Remember, grams is the unit of mass. We also have a volume of 10.4 milliliters. This is my volume. What is the density? Density is unknown. We do know, however, that density is equal to destiny breaking my heart, my mass divided by my volume, which makes one heart put together. So now I can calculate that by putting my mass, 11.29 grams, over my volume of 10.4 milliliters. I'm going to take that number 11.29 and divide it by 10.4, and I get 1.08557692 grams per milliliter. Oh yeah, I'm totally done. Psych! All right, we have to look at our significant figures, so always make sure to look at your significant figures. We have 1, 2, 3, 4 significant figures with our mass. That is 4. We have 1, 2, 3 with our volume. We are only as accurate as our least accurate number. Therefore, we only have 3 significant digits. 1, 2, 3. Next to the 8 is a 5. Based on our rounding rules, that 5 is going to round up that 8. And it's going to round it up to a 9. So our final answer is going to be 1.09, right? That 5 rounds up that 8. So if you remember your rounding rules, you have to remember all these little things that you were taught back in middle school, right? In high school, is that rounding. If it's 5 or above, you round up. If it's 4 or below, leave it alone, right? So we got 1.09 grams per milliliter as our final answer. That's what our density is equal to. If you leave me and you say, okay, 1.09, just like that, that is incorrect. Even though I know you're saying density is equal to this, but this tells me that you have no idea what the units of density is. You have to make sure you write your units down. Not just for this problem, but for all the problems that you're doing, you must include your units. No units means it's a wrong answer. So always include your units in your work. All right, let's see how we did. Oops. 1.09 grams per milliliter. All right, check. We did good. It's always good to check when you do something wrong, or even if you did it correctly, did you do it correctly? Or if you did it wrong, how did you do it wrong, right? It allows you to actually learn. All right, here's another problem. An antifreeze mixture has a density of 1.06 grams per milliliter. If you measure out 600 grams of the solution, what volume will it occupy? Okay. This is what a lot of people struggle with, is now converting, not converting, but manipulating your equation to get what you actually need. So remember, this is our original equation. Density is mass divided by volume. But the manipulation of our equations is not that difficult. Okay. This one wants the volume, right? We're looking for this. This is what we want. We can't leave it at the bottom because it's what we want. We want it to be in a V equals format. So multiply both sides by V. V cancels out with V, and you are left with volume times density is equal to mass. Well, we're not completely done. That was just step one. Divide both sides by density. You're now left with, density cancels out with density. Volume is equal to mass divided by density. And now you could solve the problem and plug in your numbers. When you plug them in, you're going to get your 600.0 grams divided by your 1.06 grams per milliliter. Well, what's going to occur is that grams is going to cancel out with grams, and you're going to be left with milliliters, which is the unit that you want. Now, a little thing about math, because you could see this and you're like, oh my God, how does that even work, right? If your volume and your volume's at the bottom, well, isn't necessarily. You have grams times 1 over grams per milliliter, okay? 1 over grams per milliliter. Well, when you're doing this, this is the same as saying grams times milliliters per gram. Grams cancels out with grams, and you're left with milliliters. This only works because the 1 is on top of that, and you go back and you look at your multiplication rules, and boom, bada bing, explained. Okay, if you can't remember it or anything like that, just kind of remember that little trick, and then you'd be able to see that right there. Okay. Let's look at this. Hopefully you tried this problem out on your own and you got your own answer. Okay, 566 milliliters. We have 3 significant figures here, 4 significant figures right there. Yes, this is 4. There's a decimal, therefore this is 0, and all of these other zeros are significant. Remember, the zeros are significant if they are sandwiched between 2 significant numbers, just like in this one. The zero is sandwiched between 2 significant numbers, or if there's a decimal after a significant figure, this decimal is after this one. It doesn't have to be right after it. It could be anywhere after it. So this decimal is right after this significant figure. So therefore, all of these zeros count. All right, so this is 4, this is 3. Your answer has to be in 3. Hopefully you were able to do that. Aluminum has a density of 2.79 grams per centimeters cubed. What is the mass of a block of aluminum with a volume of 1.32 liters? Ooh, this is like a lab question, but let's go ahead and do it. Okay. Aluminum or aluminium, 2.70 grams per centimeters cubed. This is the density of it. What is the mass? Mass is equal to parentheses. Why did I say parentheses? To question mark. Mass is equal to question mark. And volume is equal to 1.32 liters. Well, remember, density is mass divided by liters. We're going to go ahead and solve this problem. If you plug everything in, you could go ahead and do that. I always like to have my variables solved for first before plugging in any numbers. So in order to isolate my mass, I'm going to multiply both sides by liters. Liters cancels out with liters. That just turns into the number 1. And you're left with, I wrote liters, but it's volume. I'm going to write volume just to keep it the same for you guys. The unit of our volume is liters though. But that leaves us with volume times density equal to mass. All right. Now we could plug in all our information. 1.32 liters times the density, 2.70 grams per centimeter cube, is equal to our mass. All right. Now, I want you guys to note something. What's up here? Are these units the same? I don't believe so, right? So I hope you said, no, Mrs. Valdivia, these units are different. So let's go ahead and go back a little bit and look at this unit conversion between centimeters and liters. It's right here. There is 1,000 centimeters cubed in 1 liter. So even if you solve this problem, if you didn't do this conversion, your final answer would be incorrect because your units cannot cancel out. Right? So let's solve this and leave these units, and then we're going to convert. Okay. I'm going to take my 1.32, multiply it by my 2.70, and I get 3.564 liters times grams over centimeters cubed. Obviously, that is the incorrect answer. Here is my equivalency that I need to use to solve the rest of the problem. Let's change this color. Let's go blue. Okay. I'm going to use my equivalency. I'm going to cancel out centimeters. So I'm going to put 1,000 centimeters cube on the top, my 1 liter at the bottom. Now, by doing that, I could actually cancel out some units. So let's do that. Liters cancels out with liters. Centimeters cube cancels out with centimeters cube. I love it when things work out. I'm left with grams. Yes, that's exactly what I want. Okay. I'm going to write my final answer, 3.564 grams. Is it my final answer though? Okay, we are given 1, 2, 3 significant digits. This one is in 1, 2, 3, 4. Therefore, no, it's not my final answer. I have to have it in 3. 1, 2, 3. This 4 next to the 6 cannot round up my 6. Therefore, I need to drop the 4. My final answer is going to be 3.56 grams. And this is equal to the mass. Okay, let's go back to where that question was at. All right, this one right here. Oh, did I miss a 0 somewhere? All right, let's see. What did I do wrong? I guess I did something wrong, obviously, right? We could tell. Or did they? Okay. All right, 2.7 grams. They started with a block with a volume of 1.32. Oh, okay. I see what I missed. All right. So I missed this part, and that was totally my fault. I wrote it down, but I didn't pay attention. Okay. My bad. Let's go ahead and look at this. Or did I? Let's see. 1.32. All right. And then they did their conversion. They multiplied it by 1,000. We multiplied it by 1,000 right here. All right. Liters cancels out with liters. Okay. 13.2. And then they multiplied it by their mass. And they got 3,560. I'm going to go ahead and put this in my calculator one more time. Maybe I dropped a 0 somewhere. And you know what? I should be able to see that because I'm multiplying a number by 1,000. And actually, even before I do that, this is my number. Okay. I didn't multiply it down. I just canceled out my units. I didn't even do my multiplication. Oh my goodness. right? Is this common? Yeah. As you can see, I just did it. But it's always good to double check. Does your answer make sense? So this is a good like, oh my gosh, does it really make sense? No, it doesn't make sense. Why? Well, because you multiplied it by 1,000 and you didn't finish the problem. You finished the units, but not the problem. All right. What does that get us? That gets us partial credit. But we're going to be looking at our answers because we're smart and we know that we always have to double check our work. When we double check our work, we're like, oh, I have to multiply it by 1,000. 1, 2, 3. That's going to give me 3,564. All right. Like I said, our answer has to be in 3 significant digits. There's 4 cannot round up that 6. We can't just drop it though, because now if we drop it, before I dropped it because it was after a decimal and I didn't have to include it. But now, okay, now it's not part of a decimal, it's part of a giant whole number. Okay. So now we have to either round up or round down to make it into 3 significant digits. There's a couple ways we could express this answer. One is that because it's a 4, we're going to round this one down. And this gives us 3,560 grams. We could also express this answer in significant scientific notation, and that's going to be 1, 2, 3. And you could express it this way. Okay. So these two answers are equivalent and the same. This 0 is not significant because there is no decimal anywhere in this problem and it's not sandwiched between these numbers. So the 0 is not significant, but it does tell us that we're in the thousands as opposed to the hundreds. Okay. So this answer was incorrect. The answer was incorrect because I forgot to multiply it by 1,000. All right, let's see what else we got. Okay, densities and common materials. So this is just the common densities of different metals or objects. Remember, like I said earlier, everything has a specific density. If it's unknown to us, we take the density, and once we have the density of it, we can compare it to things we already have, right? A chart, a list of everything that there is. The density of water is 1.00. What are we comparing it to? We have to always compare something to something else, right? Otherwise, it's not a comparison, it's something new. So if we're going to be comparing the density, is it more dense or less dense? Then what? In this case, water. When we're talking about density, it's always compared to water. If it's less dense than water, it's going to float. If it's more dense than water, it's going to sink. So water is our predominant comparison factor. Look at this block of wood. It has a density of 0.4 grams. Therefore, it's going to float. But if we get something with 2.7 grams, which is more dense than water, it is going to sink. Right? Kind of like things we think about but don't always think about. All right. Let's look at this problem. A rectangular object measures 3 centimeters times 2 times 1 centimeter and has a mass of 7.2 grams. What is the density of this object? And is it going to float in water? Oh, well, let's find out. An object, it measures 3 centimeters by 2 centimeters by 1 centimeter. Okay. Centimeters times centimeters times centimeters is the same as centimeters cubed. 3 times 2 is 6. 6 times 1 is 6. This gives me 6 centimeters cubed. Is it just 6? No, it's actually 6.0. So you know what? Let's go ahead and write 6.0. 6.0 centimeters cubed. All right. Now we have a volume, because remember, volume is length times width times height. And our object has a length times a width, and it has a height. We have a mass that was given to us as 7.2 grams. The density is equal to mass divided by volume. So now I'm going to take my mass and divide it by my volume. I want you guys to go ahead and do this, calculate, and see what your final answer is, and put it in the correct number of significant figures. Pause. See if you did it. All right, let's check. 1.2 grams per centimeters cube, right? Is it two significant digits? Yes. Two, two, two sig figs, and two sig figs. So your answer should be in two significant digits. Final question is, will it float in water? Well, this is more dense than water, so no, it's not going to float in water. It is going to sink, right? Well, it's not more dense, so it's not going to float. It's either going to sink or be almost at surface level, but that's a different subject. Okay, last part of our unit is our temperature. In chemistry, we love Celsius and Kelvin. Fahrenheit is usually for the temperature outside, right? But when we start thinking about science, you always hear Celsius. The freezing point of water is 32 degrees Fahrenheit. In chemistry, it's 0 degrees Celsius. The boiling point of water is 212 degrees Fahrenheit. In chemistry, it's 100 degrees Celsius. Absolute zero, negative 460 Fahrenheit, or negative 273 Celsius. Absolute zero is also equivalency to what we have, which is the another unit that's going to come up. So I'll wait for that. Okay. Fahrenheit is used for our weather, right? Or a loose conversation, as you might have. When we cook, we tend to set things in Fahrenheit, not necessarily in Celsius. Why? I don't understand why. It should be, honestly, and should be in Celsius if you ask me, because Celsius is the unit used for water. And when you're cooking, cooking is literally the control of the heat of water, right? How hot, how cold something gets based on water. If you don't have enough water, it's gonna burn. If you have water, it's gonna cook, right? So Celsius, unit created to help the measurements of water. It's perfect numbers. Okay. Now, um, okay, I would write this equation down because it's always good to have it. But Fahrenheit is equal to 9/5 Celsius plus 32. Somehow the scientists came up with this number. There's a nice explanation about it. Do we need to know it? No, we do not need to know that explanation. Just the equation is something good to have in your notes and practice some practice problems in case in the future if you do have to convert between Fahrenheit and Celsius. In this class, though, usually we're going to be converting between Celsius and Kelvin. Okay, let's go ahead and look at that. Kelvin is the other unit that we use in chemistry, Celsius and Kelvin. You might have a problem asking you to convert between Fahrenheit to Kelvin or something like that. Well, that means you're going to have to convert from Fahrenheit to Celsius, Celsius to Kelvin. Okay. All right. Kelvin is the unit that we're used for gas. When we go into the gas and we're talking about the temperatures of gas, so all your gas units should be in Kelvin. Right? You'll hear about it in my other videos. You represented a Kelvin. If you're not talking about gases, you're talking about something else, you're going to represent it in Celsius, unless otherwise stated. Celsius and Kelvin. Remember those two units. Conversion factors between Celsius and Kelvin is quite simple, simpler than the one between Celsius and Fahrenheit. 1 Kelvin is equal to Celsius plus 273.15. The 0.15 makes a big difference, so please include the 0.15 when you do your mathematics because it makes a difference in our answer. It makes us a little bit more accurate. All right, let's look at this problem. A refrigerator maintains an inside temperature of 42 degrees Fahrenheit, expresses temperature in Celsius and Kelvin. So now it wants us to just convert. Here is the unit of not the unit, the equation for Celsius to figure out what our Celsius is. So first we're going to find out Celsius. We get 5.6 Celsius by plugging it into the equation, right? Basic middle school math, right? Now we're going to use the Kelvin equation. This is all just the plug and chug. Take your 5.6 Celsius, plug it in, boom, get your answer just by adding it together. Plug and chug. Don't make it more complicated than it are. It's not actually, can't say that it already is because this is just simple, right? You have an equation, plug the number in, solve it. Calculator basically does everything for you nowadays. Right? All right. With that being said, one more time, Celsius and Kelvin are the degrees in temperature that we always want to convert with. Write these two equations down. Okay? They're the ones that are going to help you convert between everything that you need to convert with temperature related. You're going to be using these later on during gas laws. Right? So they're good to know and good to have. All right, this is it for unit conversion chapters. It was just me practicing some problems with you and dictating what we need to see when you're converting your units, not just the correct answer. We need the correct answer, the appropriate units, and the correct amount of significant figures because you're only as accurate as your least accurate number. And we don't know what you're talking about if you don't include the units. All right, you guys, see you later and good luck with everything that you're doing. Ciao.